Hello, everyone. Welcome to the final press conference of the EGU 2016 General Assembly. And this is on historical responsibilities and climate impacts of the COP21 Paris Agreement. We have 5 panelists today. Mario Kapp is a climate scientist at Climate Analytics in Berlin and at the Potsdam Institute for Climate Impact Research in Germany. Ewan Monnier is a principal research scientist at MIT at the Joint Program on the Science and Policy of Global Change in the US. Robert DeConto is a professor at the University of Massachusetts, sorry, I cannot pronounce this, Geosciences in the US. And Ben Marseillon is a professor at the Institute of Geography at the University of Bremen in Germany. And Michael Schäfer is the director and a senior scientist at Climate Analytics in Germany. And I'll hand over to our speakers who will all give their presentations. And at the end, we will open the floor for questions. Thank you very much.
Okay. Yeah, maybe you can just open that one. Great. And pass me the mouse. Okay, so here's a digested version of the presentation I gave on Tuesday at this conference. It's about the historical responsibility for climate change and how we can estimate temperature, the global temperature increase from country emissions for the global warming itself. The idea is that historical responsibility is a key concept in the equity debate to distribute mitigation efforts among countries in an equitable manner. Usually what we do to assess the climate and the projections for the near and long-term future is that we need large-scale computer systems to compute the physics within the climate system. However, regarding informing policy makers and stakeholders, it's important to simplify this kind of information and to break it down in an easy and understandable way without leaving out the essential details. The idea from the Brazilian proposal, which is closely related to the issue of historical responsibility, goes back to 1997 from the UNFCCC, and it basically says that the polluter has to pay for what he emitted. That principle states that industrialized countries, which is the Annex I countries, should bear the primary responsibility given their historical emissions. Unfortunately, the Brazilian proposal was not adapted in the Kyoto Protocol at that time, despite that it reflects that developing and developed countries have common but differentiated responsibility as it is laid down in the UNFCCC framework. Usually, how we see it, that cumulative, or what is known, that the cumulative emissions from anthropogenic action leads to a global increase of temperature, and that depends largely on how much we emit. That's why it's a big problem, and all the mitigation efforts go into the direction to reduce these kind of emissions. So there is a physical-based relationship between those two, according to the IPCC from 2013. And the projections then are based on different scenarios. Here's a low with large mitigation efforts, which leads to a lower global temperature increase than the baseline or business as usual scenario, which would lead to an increase of about 4 degrees with respect to before the industrialization. What we do here is just to re-evaluate the Brazilian proposal. It was criticized back then, almost 20 years ago, because of its the data coverage was lacking and inaccurate, and the methodology does not really reflect what is going on. But 20 days later, we are lucky enough that there is a lot of data sources on emissions. So our task was to compile these country and greenhouse gas specific emissions from different sources. These Kyoto gases consist of these 6 different gases, so carbon dioxide, methane, nitrous oxide, HFCs, PFCs, and SF6, which name is difficult to express, but these are the 6 Kyoto gases. And what Johannes Gütschow, my colleague from the Potsdam Institute of Climate Impact Research, just did is use all sources available, compile a global data set for each country, and then come up with the emissions. And here you see the total emissions of all Kyoto gases in terms of CO2 equivalent emissions. This is the share in 2012, how it is distributed among all countries or parties to the UNFCCC. You can do it for specific gases as well, so it's quite different if you look into different gases. And our idea was to derive a simple model, and I won't go into the detail how that looks like. But if you translate those emissions into the actual greenhouse gas-related temperatures, you would get something like this. So you see a large increase since the beginning of anthropogenic fossil fuel burning, which leads to a large increase in 2012 from up to 1.6 related to greenhouse gases. So it's just the positive effect of greenhouse gases. If you then say, okay, let's cut down emissions immediately, and to see how this would evolve until the end of the century, you would still see a global warming from greenhouse gases alone of 1 degree. If you then go one step further and take a look at the share amongst the countries, then you get an index of this historical responsibility. So here in that, the work, our results is that the US bears at least 20% of global Kyoto gas emissions in terms of their responsibility to temperature increases. And you can easily translate this then, as the principle states in the beginning, polluter pays. So that means, okay, if there is something like the Green Climate Fund, which collects money from the private and public sector, why not asking the US to spend 20% at least on this one to deal with climate finance and issues about this? And you see also that the EU is quite a large contributor, and the Chinese or China is also catching up. In all, you see there are a lot of developing countries already. So in terms of historical responsibility, the share between developing and developed countries becomes even more equal. And with this, I would like to end. So if you take home this graph, distribute it in any specific manner, you get some kind of measurement how historical responsibility could look like.
Good afternoon, everyone. So I'm here on behalf of my colleague Andrei Sokolov, who couldn't be here for this press conference, but I am a co-author of the study that we presented earlier this week in the conference. And so the focus of the study is trying to understand the climate impacts of the Paris Agreement. So the estimates of the impact of the nationally determined contributions on temperature have been estimated by various groups, and you see here a schematic showing the different warming estimated by different groups, and they vary quite a lot, and some of them can be either sort of the median estimate or some bounds of estimates, but it's difficult to get a clear picture of what the actual range means. And so the purpose of this study is really to investigate the uncertainty in the climate impact of the Paris Agreement. And we find that there's two major uncertainties and differences between the finding of those different assessments are driven by differences in the assumptions about climate policies beyond 2030, after the pledges actually end from the Paris Agreement, and the uncertainty in the climate system response to external forcing and strength of the carbon cycle. So our aim was to try to evaluate different extensions of the Paris Agreement versus scenarios that aim to prevent really surface air temperature from rising above 2 degrees from pre-industrial, and to try to understand what are the probabilities to stay below 2 degrees, below 3 degrees, and so on. So to do that, we use a class of models that are called integrated assessment models, that couple both an Earth system model and a model of the human activity, or global economic model. And this particular model developed at MIT has several advantages. It has the flexibility to vary very important parameters of the climate system that control how the climate is responding to changes in greenhouse gases and aerosols. And also we can look at a wide variety of emission scenarios and different implementations of policies. So to look at the question of the uncertainty in the climate system, we use probabilistic distribution functions of those key parameters that allow us to really try to understand, based on the current knowledge of the climate community, the potential for warming by the end of the century. And here you see distributions of two particular parameters. The climate sensitivity, which is the warming of the climate system if you double CO2. And the second one is the ocean heat uptake rate, so how much and how fast the global ocean is taking heat. And what we've done, because of course there's not necessarily a single knowledge or known PDF of those parameters, we looked at estimating them based on observational data sets that end in 2000 or that end in 2010 and therefore include the so-called hiatus. And so we get then two different estimates of those PDFs. So then what we did is we tried to understand the Paris Agreement in the context of a baseline scenario. And the baseline scenario we took is the Copenhagen Agreement. And you have here a set of reductions that were pledged based on the Copenhagen Agreement, targets for 2020. And so then we look at how they compare to the Paris Agreement, where the target is for 2030. There are two different types of targets. There are targets that relate to decreases in emissions of greenhouse gases, for example, the US and Europe. And you also have targets looking at carbon intensity, reducing carbon intensity. So of course, reducing carbon intensity doesn't necessarily mean reducing emissions, and so that becomes very interesting in the analysis. And so we looked at 5 different scenarios. The first one is the Copenhagen Agreement, where we assume that the countries meet the commitments submitted for the Copenhagen Accord through 2020, and there's no policy after that. We do the same thing for the Paris Agreement. We have a scenario called Paris Forever, which is the same as the Paris Agreement, but where we look at the rate at which the emissions and the carbon intensity are decreasing between 2020 and 2030, and we keep those all the way to 2100. And then a more stringent one called CAP 2050, which is the same as Paris Forever, but where we cap the emissions in 2050. And then we also look at a world where we really achieve a 2-degree warming, and we stabilize at 2 degrees. So we can see the 3 different Paris scenarios. You could see them as a pessimistic view, where after 2030 nothing happens, and a more optimistic view where sustained efforts are continued all the way until 2100. So what we find, and this is showing global CO2 emissions from 2000 to 2100. The black line is the Copenhagen Accord. The blue, turquoise, and green lines are the 3 Paris scenarios, and the orange and red are the 2-degree scenarios. You can see that certainly there's an improvement and a reduction in CO2 emissions from the Paris Agreement compared to the Copenhagen Agreement, but it's not quite getting us to where we need to be to reach 2 degrees, somewhat in the middle. So then we run the model, and we're able to look at medium values. So we have a whole distribution, and those are medium values of temperature changes. On the left, using one of the PDFs based on year 2000 data, and on the right based on 2010 data. And what we can see is that Copenhagen gets us to about 5 degrees warming from pre-industrial, and Paris is getting us somewhere between 3 and 3.5. Certainly not quite at the 2-degree targets. We can also look at that in terms of distributions. So here you can see the PDFs of the warming for the different scenarios. And I'm actually going to skip that to looking at another visualization, which is the cumulative distribution function, which allows us to determine what is the percent probability to stay beyond a certain target of warming. So you see here 2 degree, 3 degree, and 4 degree, depending on the 2 different estimations of PDF based on data going to 2000 to 2010. The point and the main finding is that there is very little probability that the Paris Agreement, whether it's the pessimistic view or the optimistic view, is getting us to 2 degrees. There's actually a 95% probability that we will exceed 2-degree warming. It's actually, the Paris Agreement is getting us much closer to a 3-degree target, with about between 20 and 80% probability to stay below 3 degrees. So these are the conclusions. What we're trying to point out is certainly the Paris Agreement was a step in the right direction. It made an impact and is likely to make an impact all the way to 2100, but it's not quite there if we really want to limit the warming at the 2-degree target from pre-industrial. And much more effort will need to take place either now or after the end of the pledges of the Paris Agreement. Thank you.
Thank you. My name is Ben Matzayon from the University of Bremen, and I'm going to discuss how glaciers would react to climate change if the Paris Agreement actually was successful. So either in a sense of keeping below 1.5 degrees or keeping below 2 degrees, and not really considering how hard it would be to get there. So we've already heard how hard that would be. And so first of all, we can actually look at projections of global glacier mass. So we are looking at the 21st century there, and you're seeing 5 different emission scenarios. The 4 ones down here are sort of the well-known one produced by the IPCC, and then we force a glacier model with that. So the dark blue line is actually corresponding to reaching the 2-degree goal. The green line is something that we sort of build ourselves because there is no IPCC scenario that would cover the 1.5 degree staying within 1.5 degrees. And we did that by scaling down the ensemble of climate runs from the RCP 2.6 scenario to reaching 2 degrees. And now what you can see is that even if the Paris Agreement was successful, glaciers would continue to melt rapidly, and in fact they would accelerate to melt for the next coming decades. And then if you look sort of at the end here towards 2100, you can see that there is hardly a difference for the glaciers between 1.5 and 2 degrees. And you could even argue, considering the uncertainties, that you have to go quite far into the 21st century to even see a difference between this very ambitious 1.5 degree goal and the business as usual RCP 8.5 scenario. Now, to understand why that is the case, so why glaciers don't seem to care very much about our future emissions, it's helpful not so much thinking about how fast glaciers are going to melt, which is what we are looking at here, but how much ice is sustainable in the glaciers in the world at certain states of the climate system. And maybe I should point out when I'm talking of glaciers here, I'm speaking of the little bits and pieces of ice outside of the Greenland and Antarctic ice sheet, and we are going to hear more about Greenland and Antarctica right afterwards. But now if you imagine you have a block of ice and you take it out of the refrigerator, it will start to melt because the environment has warmed. But depending on how warm it is and how big that block of ice is, you can maybe go back 2 hours later and there will still be a slightly smaller block of ice there, but that does not mean that it is sustainable, that piece of ice. And this is very similar to what we are seeing in the mountains at the moment. So much of the ice that we have there is just waiting to melt, essentially. And so we can look at how much ice would be sustainable. And on this graph, on the horizontal axis, you see the global mean temperature change. And on the vertical axis, you see how much ice would actually be sustainable. And at present day, we are 0.8 Kelvin above the pre-industrial, so it's this vertical line. And we have mass water stored in the glaciers corresponding to 300 millimeters sea level change. So now we can look at what amount of ice actually would be sustainable. It's this black curve. And you can see that at the moment we are very far away from this curve. So if global warming stopped today, which is physically impossible, but if it did, glaciers would continue to melt and eventually lose something like 30% of their current mass, or contributing something like 100 millimeters to sea level rise. So this is this effect that I mentioned before. The ice that we have now in the mountains to a large degree is not sustainable. It's melting, it's responding to climate change in the past, it's responding to emissions of CO2 in the past. So now we can do the same for 1.5 and 2 degrees. And you see that obviously then more ice would melt. But if you look at the right-hand side here, you can see that if we, for example, look at a 2-degree warming scenario, more than half of the entire mass that is going to melt from the glaciers is actually not responding to greenhouse gas emissions in the 21st century. It's responding to something that happened in the past, which essentially means, there are very good reasons for trying to make the Paris Agreement work, but in a sense, for much of the glaciers in many regions of the world, it's too late. We have already committed the mass loss in those glaciers. It's not yet realized. Finally, one thing that we can calculate from this is how much further mass loss we are committing for every kilogram of CO2 we emit at the present day. So also this is a function of temperature, but we can just focus at where we are at the present day. And then you can essentially see every kilogram of CO2 that we are emitting at the present day will eventually be responsible for melting between 10 and 20 kilograms of glacier. And additionally to that, it will melt parts of Greenland, it will heat the ocean, it will heat the atmosphere and so on, but this is what it will do to the glaciers. And so if you want to translate it even further, you could say, for example, if you have a more or less average car and you are an average driver, you would emit something like 200 grams of CO2 for every kilometer you go. That would translate then for something like 3 kilograms of ice lost in the glaciers for every kilometer that you move your car. So just to repeat the main messages, even if the Paris Agreement is successful, glaciers will continue to melt rapidly, and that's the case because they are responding to what has already been done in the past, so to our past emissions of CO2, and we have only relatively little leverage for the glaciers with the future emissions. And then I think it's just good to have that number in mind as a ballpark figure. Every kilogram of CO2 that we are emitting at present will eventually melt something like 10 to 20 kilograms of ice from the glaciers. Thank you.
That's great.
Hi, I'm Rob DiCanto from the University of Massachusetts, and I haven't presented this yet. I'll be talking about this tomorrow. This is a little twist on a paper that just appeared in Nature 2 weeks ago, so this is timely. And what we're doing is we're looking at what mainly the Antarctic ice sheet, I'll mention Greenland, might do in the future. We're concerned about Antarctica because it's a lot of the rock, the bed that Antarctica and the Antarctic ice sits on is well below sea level. And so we're concerned that a little bit of warming can actually do a lot of damage in terms of ice sheet retreat. There is 60 meters roughly of potential sea level rise locked up in that ice sheet. Okay, so this is mainly the development and the use of numerical models and some new modeling techniques in trying to simulate the physics of these big ice masses on Greenland and Antarctica. Antarctica, again, has been a real challenge for our community because, again, a lot of the ice sheet actually sits in ocean water. It's sitting on rock that is, in many places, more than a kilometer below sea level. And that introduces some very complicated physics, interactions between the bottom of the ice and the ocean, as well as the atmosphere and the top of the ice sheet surface. So we had some success in developing a sophisticated numerical model that did a really nice job of simulating the modern ice sheet, but was not doing a good job in simulating past retreats that we know about in the ice sheet. So in the last few years, we have added some new physics to the model, mainly trying to do a better job in looking at the implications of temperatures going above freezing in the summertime, which we expect to happen in Antarctica, that will make meltwater on the surface of the ice sheet, which can get into cracks, crevasses, which can break up the floating extensions of the ice sheet that help control the flow of ice from the interior of the ice sheet out into the ocean, so-called hydrofracturing. And we've seen events like this where extensive ice shelves have broken up very suddenly when they become covered with meltwater. We're worried about those kinds of conditions beginning to appear more frequently in the future. And some other physics having to do with looking at the structural collapse of pieces of the ice in contact with the ocean that make big vertical ice cliffs, a condition that is rare in the world today, but could become more prevalent in Antarctica in the future given enough warming. So some new physics have been added to the model. And what happened with the addition of these physics is we were beginning to be able to capture successfully past ice sheet retreats. This gives us more confidence that projections moving into the future we might be able to have a little bit more confidence in. So testing the model against these past retreats and now running ensembles of models with slightly tweaked and changed physics. So many simulations going into the future following these so-called representative concentration pathways, the RCPs that we just talked about. I'm showing results here from 3 different sets of ensembles looking at the RCP 2.6, again, that we just heard about, with very aggressive reductions in emissions, a sort of more moderate RCP 4.5, and then the red is the RCP 8.5, the so-called business as usual case. Now, looking at what happened in this new model to the Antarctic ice sheet was that it is shown that there's a potential, and these are not hard and fast numbers, they're just we're still taking baby steps in all of this, but it's suggesting that we could see up to 1 meter of potential sea level rise by 2100 just from the Antarctic contribution, not the mountain glaciers, not Greenland's contribution, and not ocean warming effects on sea level rise. The RCP 2.6, with the aggressive reduction in emissions, almost no response of the ice sheet. So that's the good news. So you could think of this as, policy still having a very, very critical role to play in all of this. Now, what's important about these results relative to the thinking even as recently as the IPCC AR5 report is that at that time, the general consensus was that Antarctica might not contribute much to sea level rise on that 2100-year time frame. Now we're talking about the potential for a meter that would need to be added on to the previous estimates, which puts, adding these new simulations onto what we saw in the IPCC AR5 puts sea level potential in the worst case scenario almost off the chart here, okay? So now what I'll talk about tomorrow is looking at, and this is all published and you can look at the paper in Nature, is what COP21 really means to this. So I have really crudely, and it's really great I'm meeting these colleagues here, I can learn a little bit more about what COP21 really means in terms of temperature change. I just went to Climate Action Tracker, one source of information about temperature relative to the COP21 commitments, and I have altered the RCP scenarios that I ran for the paper that appeared in Nature, and I'm basically letting the model evolve into the future and then capping the global mean temperatures at either 2 degrees or 2.7 degrees. And that, according to Climate Action Tracker, is where we actually stand today, assuming that everyone follows through with their agreements. And we see if that has any impact. And what we found was that the 2-degree limit simulation, it happens to be very close to the result that we get from RCP 2.6, which isn't surprising. We get very little response of the Antarctic ice sheet in the future. The problem is that 2.7, where things stand now, we get a very big response. It's 80 centimeters or so of potential sea level rise if we go to 2.7 versus 2. So there's threshold behavior in the Antarctic ice sheet system. We don't know exactly where that line is, but according to these results, somewhere between 2 degrees and 2.7 make a very, very big difference in terms of future sea level trajectories. And what's really important to note is, again, because this ice sheet is sitting in ocean water, the ice that's lost has to regrow in the ocean, which means that it might take millennia, as long as it will take for the oceans to cool back down again for the ice to heal itself and to grow back. So this is a very long-term commitment in terms of what we might lose. So you could say, according to these results, and it's still preliminary, that 2.7 degree number might not be enough in terms of commitment to really serious sea level rise. I'll end there. Thanks.
Thank you. I think I will build a little bit on what the previous two speakers have said. I will come back actually to their research in my talk. As Barbara said, my name is Michiel Schäfer. I'm the science director at Climate Analytics. Climate Analytics is a research institute based in Berlin. We do climate research, but we also do climate policy analysis. So, for example, the Climate Action Tracker is one of our projects. Nice to meet you. Now, today we have a study out in Earth System Science by my colleague Karl Friedrich Schleusner, who could not be here because his wife is actually defending her PhD. And so they're very excited and busy with other stuff. Now, the Paris Agreement, as we all know, it has formulated a limit to global mean warming of 2 degrees above pre-industrial, but well below that level, and also pursue efforts to limit to 1.5 degrees, and noting that it would significantly reduce the risks and impacts of climate change. We have looked at the evidence basis for that, and we started a long time before Paris, but it's interesting that now that Paris is agreed, that this question becomes even more relevant. Now, what did we do? We looked systematically at the difference between those levels of warming in a bunch of key impact indicators, several climate extreme events, water availability, crop yields, risks to coral reefs, as well as sea level rise. And based on an assessment of existing projections by the kind of GCMs, global circulation models, CMIP5 in the fifth assessment report of IPCC, so existing projections as well as impact models, for example, for agriculture and for hydrological cycle. Now, what we see is that if we take a regional perspective, we see significant differences at the regional level for all of these indicators that we looked at.
It's not your screen. I just realized.
Ah,
You can either use the mouse or you can tell me.
okay. Okay, no, it's okay. I'll use the mouse. Thank you for saying that, because I have more than one slide. So I will actually go to the summary first, and then dig into some of the details. Like I said, if you look at region and impact-specific, indicator-specific aspects, then you see key differences. For example, if you look at temperature extremes, then this range between 1.5 and 2 degrees marks a transition from these extreme events like dry and wet and hot events that are either still near the edge of historical observations or are really a new, let's say, climate normal regime, particularly in tropical regions. For tropical coral reefs, we see that a large majority of the reef locations in the world is at a large risk at 1.5 degrees, but all of the locations are at risk under a 2 degrees level. For crop yields, we see significant differences, in particular for tropical maize and wheat. For regions like West Africa, Southeast Asia, Central America, as well as the north of South America. Now, what we learn from this is that its particular hotspots of change emerge in the tropical regions if we look at this difference between 1.5 and 2 degrees. Now, I want to make a quick excursion here, because we looked at 1.5 and 2 degrees levels, and I noticed previous speakers also speaking about this difference, and also about using RCP 2.6, the lowest AR5 scenario, as a proxy for 2 degrees. I think it is a very valid proxy for well below 2 degrees. So the interpretation of the Paris Agreement is very important here. If you look at the climate models of the IPCC AR5, you see that in RCP 2.6, the global mean warming by the end of the century is roughly 1.6 degrees above pre-industrial, so very close to 1.5 degrees. So if you compare RCP 2.6 to a 1.5 degree scenario, one might not see a significant difference. So it's interesting to see, as Professor De Conto just mentioned, that if you look at other, let's say, specific 2-degree level, then you might see a bigger difference or still no difference at all. We looked at specifically 2 degrees and 1.5 degrees, so not RCP 2.6. Now, just some examples here. If you look at warm spells, at the maximum temperature in a year and how that increases, then we see that this increase in the duration of heat waves is up to 1 month under 1.5 degrees and 1.5 months, under 2 degrees. And so a factor of 50% longer. And the same in tropical regions, except they're longer to start with, even under 1.5 degrees. There's a big change in annual water availability for irrigation and residential sectors, in particular for the dry subtropical regions like Central America and South Africa. If you look at heavy precipitation days, we see again a significant increase between 1.5 and 2 degrees, this time especially for high latitudes as well as monsoon regions. We looked at the global sea level rise, and we did not include here the kind of very recent assessments that the previous 2 speakers explained. And we see there 40 to 50 centimeters under 1.5, 2 degrees. It does, however, confirm this difference, that there is a relatively small difference, as also shown by Professor De Conto, between 1.5 and 2 degrees. What is important, though, is also to note that by the end of the century, there is, of course, a difference in the rate of sea level rise, which starts to become significant. And that is some indication for the long-term sea level rise commitment. And then finally, we looked at coral reefs, and here it's a very bleak picture where 90% of coral reefs would already be at risk under 1.5 degrees by 2050, and almost 100% under 2 degrees. And 2 degrees that would remain until the end of the century, but in 1.5 degrees, in the scenarios that we used, we see that there's actually a reduction in the risk level by the end of the century. So that could offer some kind of a window for adaptation, or perhaps if resilience is on the upper edge of current estimates, then coral reefs at many locations might hang out until the end of the century and beyond. Now, my final slide. Can I go back? Can you go back? Yeah. Thanks for pushing that button. Sorry. So one further. There we go. So this is just to show you the background of this, because we looked at, I showed you some of the global results and some of the sensitive regions, but if you look at really what we did, we looked at all these 26 individual regions in our analysis, and we built these cumulative distribution functions of probability of certain indicators. In this case, we looked at consecutive dry days, so the number of days that precipitation is below 1 millimeter per day. And we constructed these CDFs for the present day, and then blue for a 1.5 degree scenario and red for a 2 degree scenario. And then globally, you see very little difference at the typical year, but the dry years, they shift towards even drier in many locations globally. And if you, for example, zoom in a particularly sensitive region like the Mediterranean, then you see that there's a shift in the 50% probability towards much drier conditions. And then again, a larger shift on the very dry side compared to the somewhat wetter side. I think I will leave it at this. So this is the underlying basis of those more general statements at the global and regional level. Thank you.
Thank you very much. I should mention the study should now be available on the Earth System Dynamics website, which is one of the EGU journals, and the press release will be on the EGU website. Thank you very much for your presentations. We'll now open the floor for questions. Are there any questions from here in the room?
Hi, can I ask Mario? Oh, Andy Coghlan, new scientist. Can I ask Mario? I mean, I think it's the first time I've seen the contributions of different regions of the world all mapped out so graphically. I mean, what do you think the outcome should be in terms of how those countries actually, if you like, pay for that?
Yeah, thanks. It's a good question. Coming up with results is easy as a scientist, but guessing the implications is quite difficult. And I guess there will be a lot of debate what to do if you have these kind of numbers. I mean, usually people or countries are struggling and they would like to negotiate to do as less as possible in terms of how much it costs, how much is affordable to them. So, I mean, developing country usually have lower or if they have lower responsibility, they should do even less. And the large bearing of these mitigation efforts should definitely be on the developed countries. But one idea of the Brazilian proposal was actually really just come up with historical responsibility, as we just showed, and use these indicators to split it in a fair way for those who have committed too much emissions in the past. So that's the general idea. Of course, you can also translate it into mitigation efforts of greenhouse gases. But there you have to see, okay, this is a long-term process. If we think of 2100, it makes it much more difficult to plan for a reduction in greenhouse gases. And of course, nobody or everybody sees that the efforts in becoming climate neutral or CO2 neutral is large, but this is the first step to start seeing what is the basis of our discussions and what can we do about it, and this can be negotiated.
I mean, if it was a court case and you were looking for the guilty person, I mean, it's pretty kind of incontrovertible, isn't it? Who's to blame? Who should be in jail?
I wouldn't put anyone in jail. You can also see it positive that you say, okay, here, if you rank the first 3 top emitters, here's your chance to speed up and take your responsibility, and which is not always negative and should be seen positive. So I'm more optimistic in that respect than just saying, oh, who to blame. It's more like who is in favor of doing the action.
Great.
Hi, yes, Bob Berwin, freelance reporter. In terms of glaciers, Ben, are there some general guidelines in terms of geographic variability? Would it be fair to say that glaciers at higher latitudes, at higher elevations will last longer, or there'll be larger remnants as opposed to the tropical glaciers and so on?
Yeah, so as a general rule, you can say the smaller the glacier is and also the lower the mountaintop is, the more likely it is that the glacier will disappear fast, right? Because glaciers have one thing is the response time, right? In small glaciers, just like smaller blocks of ice are melting faster than big glaciers. But then each individual glacier has a very hard threshold in a sense. If the summer snow line rises above the mountain peak, there is no way the glacier can survive, right? And that means that, for example, the Alps, they have some high peaks, but not that high peaks. So glaciers will be reduced strongly there. But then there are other places, like, for example, Scandinavia, where the mountains also don't go that high. The glaciers tend to be rather flat and broad. And so those glaciers have very hard limits in terms of what temperature they can survive.
Thank you. Are there any additional questions? Yeah. Do you have one? No? If not, we'll finish here. This is our final press conference, so thank you all very much for coming, both to this one and to the other media events we've had at the Assembly. There's plenty still on offer in the rest of the conference center, and I hope to see you all next year from the 23rd to the 28th of April. Thank you very much, and thank you very much for your presentations.